When dealing with parking lot lighting circuited at 480 volt single phase, the selection of the appropriate circuit breakers is crucial for safety and code compliance. The question arises whether to use single phase or three phase breakers when the lighting is configured with 2 Hz per lamp, such as AB, BC, or COR, and the 9 circuits are grouped into 3 runs with 3 circuits each. The correct answer is to use single phase breakers. To understand why single-phase breakers are the correct choice, it's essential to delve into the fundamentals of single-phase and three-phase power systems and the operational characteristics of circuit breakers. A single-phase power system involves a single alternating current AC voltage source. In a typical configuration, there are 2 wires, a hot wire carrying the voltage and a neutral wire providing the return path. The voltage between the hot and neutral wires is the standard single-phase voltage, commonly 120 volts in residential applications in North America, but in this case, it's 480 volts for the parking lot lighting. The current flows through the load connected between the hot and neutral wires. Single-phase systems are widely used for residential and light commercial applications due to their simplicity and cost-effectiveness. A three-phase power system, on the other hand, involves 3 AC voltage sources, each with the same magnitude but offset by 120 electrical degrees. This means that the voltage waveforms are out of phase with each other. Three-phase systems are commonly used in industrial and commercial applications where higher power levels are required. There are 2 main configurations for three-phase systems, Y and delta. In a Y configuration, the 3 voltage sources are connected in a Y shape with a common neutral point. The voltage between any 2 hot wires is the line-to-line voltage, while the voltage between a hot wire and the neutral point is the line-to-neutral voltage. In a delta configuration, the 3 voltage sources are connected in a triangle shape with no neutral point. The voltage between any 2 hot wires is the line-to-line voltage, which is also the phase voltage. Circuit breakers are protective devices designed to interrupt the flow of current in an electrical circuit when a fault condition occurs, such as an overload or short circuit. They are essential for preventing damage to equipment and protecting personnel from electrical hazards. Circuit breakers are rated based on their voltage, current, and interrupting capacity. The voltage rating indicates the maximum voltage that the breaker can safely interrupt. The current rating indicates the maximum current that the breaker can carry continuously without tripping. The interrupting capacity indicates the maximum fault current that the breaker can safely interrupt. Single-pole breakers are designed to protect a single circuit and have one handle. They are commonly used in single-phase circuits to protect individual branch circuits. Double-pole breakers are designed to protect 2 circuits simultaneously and have a common trip mechanism. They are commonly used in single-phase circuits that require 240 volts, such as for electric ranges or water heaters, or for protecting 2 separate 120-volt circuits. 3-pole breakers are designed to protect 3 circuits simultaneously and have a common trip mechanism. They are commonly used in 3-phase circuits to protect entire 3-phase systems. Considering the specific scenario of the parking lot lighting, which is circuited at 480 volts single phase with 2 Hz per lamp and 9 circuits grouped into 3 runs, the use of single phase breakers is the appropriate choice. Here's why. Firstly, each of the 9 circuits is a single phase circuit, meaning that it only has 1 hot wire and 1 neutral wire, or in this case, 2 hot wires derived from different phases of the 3-phase system. Each circuit operates independently of the others. Secondly, a single-phase breaker is designed to protect a single circuit from overcurrent conditions. It will trip when the current in that circuit exceeds its rated value, regardless of what is happening in other circuits. Thirdly, using a 3-phase breaker would not provide adequate protection for each individual single-phase circuit. A 3-phase breaker trips when the current in any of the 3 phases exceeds its rated value. However, in this case, each single-phase circuit is connected to only one phase of the 3-phase system. If a fault occurs in one single-phase circuit, it may not draw enough current to trip the 3-phase breaker, leaving the circuit unprotected. Fourthly, the configuration described, with 2 Hz from different phases such as AB, BC, or CA feeding each lamp, still constitutes a single-phase circuit for each lamp. The voltage potential between the two hots provides the power, but the circuit itself is not inherently three-phase. Fifthly, using single-pole breakers for each hot wire of the single-phase circuit provides the most specific and effective protection. If an overcurrent situation arises on one of the hot wires, only that breaker will trip, isolating the fault and preventing unnecessary interruption of the other circuits. Sixthly, the National Electrical Code (NEC) provides guidelines for overcurrent protection of electrical circuits. While the specific requirements may vary depending on the application and local codes, the general principle is that each ungrounded conductor that is hot wire should be protected by a circuit breaker or fuse. This aligns with the use of single-phase breakers for each single-phase circuit in the parking lot lighting scenario. To elaborate further, let's consider a hypothetical scenario. Suppose each single-phase circuit in the parking lot lighting is rated for 20 amps. If a short circuit occurs in one of the circuits, causing the current to surge to 50 amps, a single-phase 20-amp breaker protecting that circuit will trip, interrupting the flow of current and preventing damage to the wiring and equipment. However, if a three-phase breaker were used instead, and the other two circuits connected to that breaker were operating normally, the total current draw across the three phases might not be high enough to trip the breaker. As a result, the short-circuited circuit would remain energized, potentially causing a fire or other hazards. Furthermore, consider the impact of using a three-phase breaker on troubleshooting and maintenance. If a problem occurs in one of the single-phase lighting circuits, it would be much easier to isolate and diagnose the issue if each circuit is protected by its own single-phase breaker. Tripping a three-phase breaker would shut down all three circuits, making it more difficult to pinpoint the source of the problem. In addition to the electrical safety considerations, there are also practical and economic factors to consider. Single-phase breakers are generally less expensive than three-phase breakers, making them a more cost-effective choice for this application. They are also more readily available and easier to install. It is also important to ensure that the circuit breakers used are properly sized for the load they are protecting. The current rating of the breaker should be matched to the ampacity of the conductors in the circuit, as specified in the NEC. Using breakers that are too large can result in inadequate protection, while using breakers that are too small can result in nuisance tripping. When installing or maintaining electrical systems, it is always recommended to consult with a qualified electrician or electrical engineer to ensure that the work is performed safely and in accordance with all applicable codes and regulations. They can assess the specific requirements of the application and recommend the appropriate components and wiring methods. In summary, for parking lot lighting circuited at 480 volts single-phase with 2 hots per lamp and 9 circuits grouped into 3 runs, single-phase breakers should be used to provide adequate protection for each individual circuit. This ensures electrical safety, facilitates troubleshooting, and complies with the NEC guidelines. Using three-phase breakers in this scenario would not provide the same level of protection and could potentially create safety hazards. Remember to always prioritize safety and consult with qualified professionals when working with electrical systems. Always de-energize circuits before working on them and use appropriate personal protective equipment (PPE). It's also important to note that while the term single phase is used to describe the individual circuits feeding the lamps, the power source itself is likely a three-phase system. The 480-volt single phase is derived from 2 legs of the three-phase system. This is a common practice in commercial and industrial settings to balance the load across the 3 phases. Each single-phase circuit, however, only uses one phase at a time relative to another phase, making single-phase breakers the appropriate choice for overcurrent protection on each individual circuit. If the scenario involved a true 3-phase load where each phase was actively used in a balanced manner, a 3-phase breaker would be required. However, since each lamp is wired in a single-phase configuration despite being derived from a 3-phase source, the protection strategy should reflect that. The NEC Section 240.4 D addresses the protection of small conductors and requires that they be protected against overcurrent in accordance with their ampacities. This is further emphasized by NEC Table 310.15. B16, which lists the allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, not more than 3 current-carrying conductors in a raceway or cable or earth directly buried, based on ambient temperature of 30 degrees Celsius. These tables help to ensure that the selected breaker size does not exceed the conductor's ability to safely carry current, preventing overheating and potential fire hazards. When selecting a circuit breaker, it is also important to consider its interrupting rating, which is the maximum fault current that the breaker can safely interrupt without being damaged. The interrupting rating should be equal to or greater than the available fault current at the point of installation. The available fault current can be calculated using various methods, including using a fault current calculator or consulting with an electrical engineer. The NEC requires that circuit breakers be marked with their interrupting rating. NEC Section 110.9 states that equipment intended to interrupt current at fault levels shall have an interrupting rating sufficient for the nominal circuit voltage and the current that is available at the line terminals of the equipment. Equipment intended to interrupt current other than fault levels shall have an interrupting rating sufficient for the current that must be interrupted. The circuit breaker's interrupting rating is typically found on the breaker's label, expressed in kiloohms Ka. Standard interrupting ratings for molded case circuit breakers are 10 Ka, 14 Ka, 18 Ka, 22 Ka, 30 Ka, 42 Ka, 65 Ka, 85 Ka, 100 Ka, and 200 Ka. In addition to the interrupting rating, it is also important to consider the circuit breaker's short circuit current rating SCCR, which is the maximum short circuit current that the breaker can withstand without being damaged while it is in the closed position. The SCCR is also typically found in the breaker's label and is expressed in kiloohms Ka. The SCCR of the circuit breaker should be equal to or greater than the available fault current at the point of installation. NEC Section 408.6 requires that switchboards and panel boards have a short circuit current rating not less than the available fault current. Understanding these ratings and ensuring they are adequate for the installation is paramount for preventing catastrophic failures during fault conditions. Further, coordination studies are often conducted for complex electrical systems to ensure that overcurrent protective devices trip in a coordinated manner. This means that the device closest to the fault should trip first, minimizing the impact on the rest of the system. Coordination studies involve analyzing the time current characteristics of the various overcurrent protected devices in the system and selecting devices that will trip selectively. Selective coordination is particularly important in critical facilities such as hospitals and data centers, where it is essential to maintain power to essential loads during a fault condition. There are various types of circuit breakers available, each with its own advantages and disadvantages. Molded case circuit breakers MCCBs are the most common type of circuit breaker and are used in a wide range of applications. Insulated case circuit breakers ICBs are used in high current applications and have a higher interrupting rating than MCCBs. Air circuit breakers ACB are used in very high current applications and are typically used in main distribution panels. Electronic trip circuit breakers use electronic sensors to detect overcurrent conditions and offer more advanced protection features than traditional thermal magnetic circuit breakers. Arc fault circuit interrupters of size are designed to protect against arc faults, which are dangerous electrical faults that can cause fires. Ground fault circuit interrupters GFCIs are designed to protect against ground faults, which occur when current leaks to ground. GFCIs are commonly used in wet locations such as bathrooms and kitchens. The selection of the appropriate type of circuit breaker depends on the specific application and the level of protection required. When working on electrical systems, it is crucial to follow safe work practices and use appropriate personal protective equipment (PPE). This includes wearing insulated gloves, safety glasses, and arc-rated clothing. It is also important to de-energize circuits before working on them and to verify that they are de-energized using a voltage tester. Working on live electrical circuits is extremely dangerous and can result in serious injury or death. In summary, the use of single-phase breakers for the 480-volt single-phase parking lot lighting circuits is the correct approach. This ensures that each circuit is individually protected against overcurrent conditions, promoting safety and preventing damage to equipment. Understanding the principles of single-phase and three-phase power systems, as well as the characteristics of circuit breakers, is essential for making informed decisions about electrical system design and installation. Always consult with qualified professionals and adhere to the NEC guidelines when working on electrical systems. Remember to prioritize safety and use appropriate personal protective equipment (PPE) to protect yourself from electrical hazards. By following these guidelines, you can ensure that your electrical systems are safe and reliable.